Hello, today we're going to look at a very important part of mathematics called differentiation. We're going to kind of explain where it comes from first principles, which it kind of sounds quite fancy, but it basically just means I'm going to kind of explain the logic behind differentiation and show you how to find the differential of something using this idea of first principles. So let's start off imagining we've got a function, y equals f of x. So just a general function, and I'll draw a quick axes. So let's swap colour as well. So let's say we've got a function something like this. So it's a curve, which means the gradient is changing all the time. So it looks like it's quite straight here, but it's curving all the time upwards that way. So the idea of differentiation is that it will give us a way of finding the gradient of the curve at any point. We just say what point we want, what x value, and the differential, or sometimes it's called the gradient function, will tell us the gradient. So let's start off by picking a point. So let's call this point x here. So the value of the function at x is f of x. Okay, that's our y value, f of x, there. And we could find the gradient of this by doing, well, let's pick another point. Let's say we pick a point over here, and a bit of a weird way of defining it, but we're going to say this point is x plus some extra. We're going to call that a. So this point is just a extra on from there, or like the gap between them is a. And the value of the function here will be f of x plus a, because we're going to put that into our function, and that will give us the value. So like I said, we could find the gradient here by just doing this. So kind of imagining taking this line here and extending it on as well. Can't really draw very straight lines, but you hopefully get the idea. It's a line that goes through these 2 points, and you can see that at f of x it actually is kind of close to the gradient, but it's not that good. I mean, it'll be a rough approximation. I'd say the gradient probably is a little bit steeper than our line. So we could do this to find the gradient. How we'd actually work it out, we'd have to go, just like if you were doing it on a straight line, we'd have to do the change in y over the change in x. So change in y over the change in x. Okay, and in this case, well, what's the change in y? Well, that's the difference between these 2 points. So that's f of x plus a minus f of x. So that's our y values changing. So we need to work out what the x value here was. Well, that was x plus a. And then take away the x value of the other point, which is that. So we can simplify this down a little bit and get f of x plus a minus f of x at the top. But at the bottom, we've got x plus a minus an x. So that's just a. So this would tell us the gradient. I could pick 2 points, I could work out what that was, I could find the gradient. But it would only be an estimate. It wouldn't be a particularly good estimate either, because as you can see, the line that we've drawn here between these 2 points, and I've extended it on a bit, it's not that close to my pink line. It's quite close, but it's not that good. So the kind of idea of this differentiation is thinking, well, how could I improve it? How could I make that a better estimate? And hopefully you've kind of spotted that this gap is really, really important with our estimate. If I instead took this point, and now this was my x plus a, then the line that I draw here will be a better estimate for my gradient. Hopefully the diagram's not getting too messy, and you kind of get the idea that as I decrease this a, as this gets closer and closer to x, my estimate is going to get better and better. And if I picked my point A to be at the tiniest little gap after x, that would give me a really, really good estimate. And that is the idea of this differentiation. What we do, and this is a really important idea, a really important equation to remember, is we take what's called the limit as a tends to 0 of our gradient. So we know the gradient is f of x plus a minus f of x all over a. And the idea of this is we think, well, if a is, that gap is really, really, really small, it's basically 0. And we think, well, what does that look like for our particular function? So it probably doesn't make much sense at the moment. We need to kind of put some actual functions into here to kind of get some differentials out.
Okay, I decided just to add this section into the middle of the video, just trying to explain the logic a bit better and with a slightly nicer diagram with a bit more of a curve. So basically I'm just kind of showing you again that idea of closing in the gap to improve the estimate. So let's say I wanted to find the gradient here at this point. So this will be my x. And then as before, I pick another point over here to be my x plus some a value. And you can see the gradient of the actual line should be quite straight. It should be almost a straight line, so the gradient should be close to 0. But at what I've got at the moment, if I draw this in, trying to draw a straight line is a bit difficult. I can do a better job of that. Let's try again. There we go. Something like that. So you can see at the moment the gradient of this line I've drawn here, this chord, is nowhere near as a straight line going across the page like it should be. So that's really not a great estimate. It is an estimate, I suppose. It's just not a very good one. But if I then say, well, let's imagine a is now a bit smaller. So this is my new x plus a. So I've decreased the value of a. Then the point would be about here. And then hopefully you can see straight away that yellow line is a much, much better estimate of the gradient of the actual point, the gradient at the point x, which is what we're looking for. So I've reduced the value of a, I've over halved it, and the estimate, the gradient has got significantly better. So kind of finally it's going to be a bit of a squeeze to fit it all in, but if I pick one more point, oops, let's say about here, so it's literally almost touching it. So this is my new x plus a. Then the gradient now is pretty good. It's going to be almost a straight line. I can't draw a straight line, but you get the idea with these 3 points. You can see as I decrease the value of a, that gradient gets closer and closer to being what I would imagine the actual gradient would be of the line, the purple line. That's the one we're looking for. So you can see that the idea of differentiation is reducing this value of a. As we do so, the gradient gets closer and closer, and that's where that idea of the limit comes from that we're going to use to differentiate. So let's look at some examples.
So here's our first example. And we're going to have the function y equals x squared. Okay, and we're going to find the gradient function, or the differential, for this equation. And what that will give us is we'll be able to say, well, if I want the gradient when x is 4, we put it into our function and it will tell us how steep the line is. So to do that, we're going to use this equation. So what we're going to need to work out, well, our f of x is just the same as y, so we could say f of x equals x squared. So we've got that bit, that's fine. We need to think, what would f of x plus a look like? Well, if f of x is x squared, then f of x plus a is x plus a squared. Because where we had x before, we've now got an a. If I could expand this out, I'd get x squared plus ax plus ax plus a squared. So I could write that simply x squared plus 2ax plus a squared. So we've now got everything we need to put it into this thing. So the gradient, and a bit of notation here, we normally call this gradient function dy dx, which is another way of saying that dy over dx. So let me just get rid of that dot because that shouldn't be there. That dy over dx, that d kind of stands for a little change in y over a little change in x. And if we go back to our original gradient, that's really what we're doing. So change in y over change in x. So just think of dy dx as being a little change in y over a little change in x, which is what we were doing with that really small a. So we say that is equal to the limit as a tends to 0 of our f of x plus a. What f of x plus a we've got is this. So that's x squared plus 2ax plus a squared. And then that's subtract f of x. F of x is just x squared. And then that's all over a. So the limit as a tends to 0. Now we can do a bit of simplification. So if we've got x squared plus 2ax plus a squared minus x squared, we can cancel the 2x squareds out. So we get 2ax plus a squared over a. And, well, the top, everything on the top has been multiplied by a, and everything on the bottom has as well. So we can divide the top and bottom by a, just cancelling the fraction down. So cancelling those out, we get 2x plus a. So because we've cancelled the a from that side and we've just got rid of one of the a's there, and then we're left with just one on the bottom. Now this is where we need to think about the limit. Well, if a is heading towards 0, then what would we end up with left over from this? Well, simply, we're going to have no a at all, and this 2x isn't going to change at all. So the limit is just 2x. And that tells us the gradient at any point. So if I wanted the gradient when x was 5, I would just have to do 2 times 5, and that would give me how steep the line is. So yeah, really powerful stuff. Let's look at another example. Example 2. This time let's do f of x is equal to 4x. So again, we're going to use that equation. I'll just write it down again. Dy dx, the gradient function, is equal to the limit as a tends to 0 of f of x plus a minus f of x all over a. So again, we're going to need to figure out, well, what is this f of x plus a business? So f of x plus a, that just means, well, wherever we had an x before, we've now got an x plus a. So that will give us 4 lots of x plus a, which, if we expand that out, is 4x plus a. 4x plus 4a. Okay? So we're now ready to type this into our equation. So bringing that down here, we get dy dx equals the limit as a tends to 0 of 4x plus 4a minus 4 lots of x, because that's just f of x, all over a. So that will give us the limit as, just an extra line there, the limit as a tends to 0 of, well, the 4x's are both going to cancel out here, so we're just going to be left with 4a over a, and in fact the limit as a tends to 0 of this, well, it's just going to end up being 4 over nothing, because the 2a's are going to cancel, so it's just 4. So the a doesn't even really come into this at all. The actual gradient function is just 4. And hopefully you can kind of imagine what that line looks like. It's going to look something like this. It's just a straight line, and well, we know it's going to cross through 0, 0, and we could pick another point here, so that could be 2 and 8. And so if we wanted to find the gradient kind of the old-fashioned way, how we would do it before, all we'd have to do is work out, well, what's the change in y here, and what's the change in x? Well, the change in x is 2, and the change in y is 8. So the gradient, if we were finding that before, without using differentiation, would be change in y, 8 over 2, which is the change in x, and just gives us 4. So it kind of works both ways. Obviously, if it's a straight line like 4x, we don't necessarily need to do the differentiation. But if it's something like a curve like we did in our first example, then we can't do it using our kind of triangle idea. We have to do this differentiation. And that's it. Any questions, please leave them in the comments or drop me a message. Thank you.